Good morning, professors. I'm Yang Wei from the Kwun Secondary School. Today I will be talking about on polyarctic group and ordinary polyarctic equation. And this PowerPoint is divided into two main types. For the part one, it is the theory of the polyarctic group, or we call the N-Yeri group. And for the part two, that is the study of the ordinary polyarctic equation, which is OPE. And before we start, we just introduce some notations and conventions first. First, in our paper, we assume that the n is less than infinity and greater or equal to 3. And in notation 2, we denote the set 1, 2 up through the n by the in. And the in is contained in the set of natural number. Okay, then the notation 12 said that for this FFFFF on the right-hand side, we will denote it by the f bracket k, and we call it the kth iteration of the operation f.
What is f?
F is the N-Yeri operation that we introduce later. F is the N-Yeri operation f on a set S. It's a function mapping Sn to the S. It's just like the S has n elements, and we combine that n elements to form the another element in the set. And and this means the F, the N-Yeri operation that we study.
What is S1 to the n means?
S1? Which one? Sorry. Professor? X1. X1 is some element in this set. Yeah. And then we use the conventions proposed by Kwun in 1961, that for the sequence of elements xi plus 1 to the xj, we will denote it by the xi to j. And if there exists t consecutive elements x, and we will call it the tx and denote it by the bracket tx. Because this kind of notations and conventions will help us to present our ideas and more convenience. And yes, and in our paper, we just define the N-Yeri addition and the N-Yeri multiplication. And then we will introduce the definition of the N-Yeri group. An N-Yeri group GF is a non-empty set G together with an N-Yeri operation F on G, such that the following axiom, 3 axioms are satisfied. For the closure axiom, it means that the operation will combine n elements in the set G to form another element in the set G. And for the associative axiom, it means that because in our definition of group, we have the associative law. And what the thing we do is that we just extend the idea to the N-Yeri case. That means that in this kind of N-Yeri operation, you can shift it to any place that you want. And for the uniquely solvable axiom, it means that for the following equation, we have a unique solution xi in G, such that for every I is contained in the set In. And then we will introduce the definition of the reducibility. An N-Yeri group GF is reducible to or derived from an ordinary group G star if and only if the f x1 to n can be represented by the following form. Then in our paper, we just proved that the theorem 16, that if two ordinary groups are isomorphic, then the two N-Yeri groups derived from these two ordinary groups are also isomorphic. And the proof is here, but because of the time limit, we will just skip it. And the definition 17 said that give the definition of the neutral element, which is an element E is called a neutral element if it satisfies the following equation. And in our paper, we just proved that an N-Yeri group GF containing a neutral element is reducible. And I want to apologize here because our original paper and the original proof in our paper is wrong. And I want to make some amendments here. We just define the binary operation as this form. And we just consider this kind of thing. And we just expand it because we just define the binary operation A star B is like this. And we just expand it. And we use the notation 12 to group this kind of notation together. And for here, we just put one f here. And here we have -1 because we get one f from here. And we have this. And here we have n minus 2 element. Here we have one element. and then we get 1e from here. And then from the definition of the neutral element, it is equal to the x2. And here we just get this, and we just continue this progress, and then we will get our result. Because, so why do we come up with such problem? It is that in our university textbook, the usual definition of the group is about the associative law, closure, the identity element, and the inverse element. If we want to form the n-Uri group, we have to extend the identity element to the neutral element. However, from our theorem 18, that the neutral element and n-Uri group containing a neutral element is reducible. So it can be reducible to the ordinary group case. However, because from this sense, the theory of the n-Uri group is equivalent to the theory of ordinary group. So if we want to form the definition of the n-Uri group like this, it is meaningless. However, there have another definition proposed by Wibbers and Huntington. That is, it is associative and closure. However, for this identity element and the inverse element, we will just change it to the property that the xa equals to b and the ay equals to b has unique solution. If we extend it, we will get our usual definition of the n-Uri group. And in this n-Uri group, some n-Uri group is reducible to the ordinary group case. However, some are not reducible to the n-Uri group case. And then we will go to the skew element, which means that for the following equations, there exists a unique solution set in G such that the following equation is satisfied. And we call this set as the skew element of X, or we call it skew X, and we just denote it by the bar X. And in 1928, Dalton just proved the theorem for 24 that the Dalton's identity, which means that in the n-Uri operations, the F is on the leftmost or the rightmost, and we have one skew X, and we have n minus 2X. Then the product is Y. And the proof is simply just here. But because Dalton proved this theorem in his German paper, so in our paper we just give a reproof here. And then we will move on to the Hossu-Gaskin theorem. One should be noticed that is if an n-Uri group point is a non-empty set together with an n-Uri operation F. If an n-Uri group point GF is an n-Uri group, then it is the condition 4 is satisfied. The fx1 to n can be represented by the following form. And in our paper, we just give an example to prove this condition. And another thing is that in our paper, we just introduce the ordinary polyadic equation. For the polyadic equation, we just give a classification that for the ordinary polyadic equation, it is containing only one independent variable. And for the partial polyadic equation, it contains more than one independent variable. And in our paper, we just focus on the ordinary polyadic equations. And the definition of it is an ordinary polyadic equation is an identity that relates the independent variable x and the elements in x and the n-Uri operations. And the general form of the OPE and ordinary polyadic equation is of this form. And we call it the kth iteration ij up through pq, nth degree the OPE. And because the kth iteration is about the iteration of f, and the ij up through pq is the place that the independent variable are. And here in our paper, we just proved that the first iteration linear OPE and the kth iteration linear OPE has an unique solution. And for the skew polyadic equation of this form and the n-Uri power OPE of the following form, we have some explicit solutions. And that's all I want to say in this presentation.